As a power switch and a command switch. And when the command switch is operated, these two switches, the power and the command switch are on. These two switches automatically close, and you get a command signal, okay, or for something. It could be a display or something, doesn't matter. Okay. So there's two top-level faults. An inadvertent command signal or no command signal. So these are kind of complementary, and that's why this is an interesting problem. The inadvertent command signal could be that we have power on. These are the things that have to happen. The power's on, relay 1 and 2 both have closed. The power switch is closed by a human operator. Command switch is inadvertently closed by the human operator. I probably should have copied this over. This command switch right here is inadvertently closed because that way we get an inadvertent signal. And so command and power switch could be inadvertently closed. Wow. Command switch fails closed, power switch fails closed. Now, rather than doing this as a fault tree, what we could do is look at this as all of the things, the sets that can happen that this fault will pass. So A, B, and F. Okay. So that if B fails closed and the power switch is closed. So actually, let me do this. So A, the power switch is on. B, the relay 1 fails closed, so that closes that circuit. And F, the power switch is inadvertently closed because power's on, power switch is closed, relay 1 fails closed, and that is sufficient for an inadvertent command signal. Okay? Because if that fails closed, it doesn't matter what the command switch is doing, it will complete the circuit, okay, and send a command signal. And then another set is A, C, and F. All of these, notice, have A. So we'll just forget about that. It has to have power to the circuit, that's obvious. Okay? But let's look at C. Relay 2 fails closed, and the power switch is inadvertently closed by the human operator. B and D is relay 1 fails closed, and the power switch is normally closed by a human operator. So, and that's another distinction that I'm not sure I agree with, because normally closed and inadvertently closed, it has to do whether or not it's appropriate, and the outcome is an inadvertent command signal. So I wouldn't think that if it's an inadvertent command signal, that would be a normal operation by the human operator. So that one I question, let's put it that way. But like I said, this is Roland Moriarty's analysis. And so where was I? B and D. C and D is relay 2 and normally closed. So I think that the D and F are redundant. So anything that has F and anything that has D, I think are redundant. Okay, so let's look at A, F, and G. Okay, F is the power switches inadvertently. Okay, so A, D, and G, once again, those are, with G we're saying command switch fails closed. Okay, now that I can believe. But the power switch, once again, D and F, these two are redundant for D and F. It has to be an inadvertent closure, I think. So then we've got B and H and C and H. B is fails closed and power switch fails closed. Okay. Where was I? C and H is 2 fails closed and power switch. And then E and G, command switch inadvertently and command switch fails closed. Okay. So the inadvertent closure by the human operator and failed closure is, I believe those, but the normally closed is probably, I don't think it's necessarily an appropriate analysis for an inadvertent signal, because that would mean that unless there's only one way we could look at it where this would be appropriate, and that's where the human operator closed it normally, thinking that it should have been turned on. Whereas here she just kind of bumped it. Okay, they closed it without intending to close it. Here they intended to close it, but they had the wrong information. That might be a way to interpret their analysis. Okay. But these are our cut sets, assuming that that's what they mean, so that we can maintain our analysis here. That's a set of cut sets which are which are no longer than three components. And if we take power along, assuming that that has to be there, then it's reduced to 2 components. Sets of 2 components. So then A, like I said, normal event. D, F, and H appearing. So D is normal. Okay, like I said, that's normal. But if it's normal, it can't result in something bad. It has to be something that is a wrong interpretation. So I don't think I don't necessarily agree with that. F and H are abnormal, okay? And then B, C, E, and G are, so F, H, B, C, E, and G is F, H, and B, C, E, and G. In other words, essentially everything except for the switch normally closed that we analyze as an abnormal situation. Okay. To me, the D is a problematic inclusion in this, because if it's normal, there's something abnormal about it, or else it wouldn't be an inadvertent command signal. It's a human interpretation error, it's a decision error, or something like that on the part of the human operator. So, and then the second one that is no command signal at all. Okay, and essentially no command signal at all is the opposite. The power is off. Not A, not B, it fails open, not C, that fails open, not D, not E, not F, not G, not H. And for it to fail, to have power to it, any one of those will result in that failure. So it's 8 non-redundant cut sets, but they're just one item to each one. Okay. But as you can see, the choice of the top level fault is going to influence your diagram and your cut sets pretty substantially. So you have to be sure that that's the fault that you really want to analyze. Does that make sense? See where I'm getting at? Okay, good. This is kind of just his analysis. All right, so that's what I wanted to say about fault trees. Okay, so we'll talk about quite a bit more next week with the problem sets, the practice problem set and the one for this topic. All right, the next topic I want to talk about, and which you hear all the time in system safety, is the inductive technique called failure modes and effects analysis, FMEA. Okay. This is kind of a brainstorming approach where you end up listing everything that can go wrong, what makes it go wrong, and how to fix it. It requires a lot of knowledge of the system. Well, all of them do really, but this one particularly, and it's best done with a group, because an individual will not think of an exhaustive list. And because of that, it tends to grow. Failure modes and effect analyses tend to grow and mature over the life of the system, as the system is better understood. And hence you start out with historical data, what everybody knows about it, or what has been documented about the system. So the idea is that we have component identification, minimally, the failure mode of the component, failure effects of each component, hence failure modes and effects analysis, and how to control for each one of those failure modes and effects that you do about it. This is kind of redundant, but there's more information that's available to you. This is an example of a component failure mode, failure effect from Roland Moriarty. Now they don't have a control in this. And again, this is one of the multiple variants that you'll run into in something. But here, see, it's a list of the components. How it can fail, whether it's open or closed, motor fails to function, coil open or closed, pressure is it high or low, tank, normal overpressure, et cetera, et cetera. So you have all the components, everything that can happen to them, and what the outcome of each one of those modes will be. Doesn't tell you what to do about it. Now, this is from another source where they have the component. This is a flashlight, so this is really kind of pretty intuitive. Okay? It's a simple system. You have the bulb, the switch, the contact, and the batteries. Not much else you can go wrong with a flashlight that I can think of anyway. And then what can happen to the bulb, what can happen to the switch, what can happen to the contacts, and what can happen to the battery. And what the effects of each one of those are, and what to do about it. Okay? I like this one because it's exhaustive. It's a really simple system that everybody's familiar with, and you can see really how the best way to do a failure modes and effect analysis is. And you can also appreciate that for something that's really complex, a very, very complex system, how tedious and long this is going to end up being. You have to organize it somehow with systems and subsystems in order to have it make any sense at all. And how also it has to be a growing, living document in the parlance of, I guess that, what is that, ISO 9000 or whatever we're conforming to now, 9001, so that it has to be a document that is subject to revisions periodically as you learn more about your system. This is one I ran into. I just did, the usual Google search of failure modes and effect analyses. And I ran across this, and I thought, well, this is kind of interesting because it's another variant on it, and it makes sense. This is a risk actuator for a spacecraft, and so I mean that's kind of interesting in itself. But the way they laid it out is different. Identification of item or function. Okay, where they have the item there. They have the failure. A mode, B cause, and then, okay, so the failure mode and the cause are in the same column, and they are labeled A or B. Then the effect is at 3 different levels: local or subsystem, next to a higher level system, and for the mission. Okay, that was kind of interesting. And then they have some severity category. It doesn't matter what it is, but that would be meaningful if you were, had a set of severity categories that were meaningful for you. And then you have a remarks section and a method that is a way to comment on the entire analysis, on the entry. So again, this is different from this, is different from the one on the previous page, but they're all failure modes and effects analysis. Essentially what it is you take an inductive approach and then you adjust it to your own needs. This obviously, whoever did this had specific requirements from their system that they wanted to, and they wanted to tweak the FMEA so that it would be more useful for them. I don't see anything problem with doing that. I mean, that's reasonable to do that, and it's nice that the system is, or that the technique is flexible enough that you can do that with it, and it's not going to have any effect really. So, an inductive technique. That's what's that's essentially what this is, where you document the modes and effects and what to do about it, and then some bearing on that, and you keep adding to it as you learn more about the system. how people can, I mean, some people can wax poetic about failure modes and effects analysis for hours and hours. I fail to see how to do that because it's such a simple approach that it doesn't really warrant a lot of attention other than the fact that it's ubiquitous, it's used everywhere. And that's what's important about it, is how commonly it's used. So it's important to know what it is and how to apply it. The next one, and there's an entire mill standard for this one, okay? It's the failure modes, effects, and criticality analysis. Now, basically what this is the failure modes and effects analysis with probabilities built into it. Okay. It's also inductive, and you look at failure modes and effects and the probabilities of each one. This is some FMECA worksheet elements that have been suggested. And I think this, if I remember correctly, I got that from the Mill Standard. And you all know, right, that you can just download the Mill Standards and PDFs. They're free. They're easy to get a hold of. These are some things that they suggested. And also, the component function is something different than we looked at before. The system and subsystem mode is maybe a little bit different. The failure level is different. Controls is the same. And applicable standards and regulations. But again, you could just as easily, without the probabilities, you could just as easily make the system an FMEA. You just don't have data on probability, and it would be fine. So, the criticality analysis is based largely on failure rates. This is kind of just extra stuff, but this is where it gets right down to. It gets down to the nuts and bolts, so to speak. The criticality for a particular mode is a product of the part failure rate. This should look really familiar to you guys by now. The duration of the phase that operates in, that should also have some familiarity. The probability of the failure mode, they call it the failure mode ratio. That's a complete misnomer. I don't know who named that. It's not going to be a ratio, it's going to be a proportion, really. And proportion and ratio is different, quite different. And also, again, conditional probability on alpha of the effect on the system. Okay? Now, and another thing that I find very interesting about this is that they have lambda and the time, but they don't use the exponential distribution. They just multiply them all together. Okay. This is the method. And then you take all of your items and you calculate each one of them for each of your items, and you sum them all up and say that's my overall criticality. So let's look at an example. Here we have 4 different categories, and once again, Mill Standard 1629 dictates these categories where 4 is minor and 1 is absolutely catastrophic, the worst thing you can imagine. Everybody run to the hills. Okay. So, this is our scenario. Okay, we have some resistor on a missile, and it could have, and that resistor, R6, has a failure rate of 1 in 100 hours. Okay? If the resistor fails, so this is a conditional probability, because if the resistor doesn't fail, this doesn't happen. It fails operational 70% of the time and non-operational 30% of the time. So it can fail, and 70% of the time the system's still functional. Okay? It's somehow built into it. Okay? And I'm not going to get into the missile construction since I don't know anything about it. Okay, so somebody else can tell me about that. But apparently that's the way this works. Okay, so now if it fails operational, it is unable to launch a missile 30% of the time. It explodes in the tube 20% of the time, and there's no effect 50% of the time. Okay, so that's the bad part, I think. And if it fails not operational, the performance of the missile is degraded 50%, and it inadvertently launches 50%. So a lot of bad stuff that can happen if that resistor fails. Okay? And the mission time is 1 hour. We're just going to assume mission time is 1 hour. Okay, so this is our failure rate. This is lambda for the missile, for the R6. This is the T. This is alpha because that's our 70%, is 0.7 for failing open. In other words, it fails operational, and 0.3 for failing closed, which is non-operational. I probably should make that a little bit more descriptive, but operational, non-operational. And then if it fails operational, these are our betas, because there's 3 outcomes. If it fails operational, and if it fails non-operational, those are our betas, our 3 outcomes, or 2 outcomes. This is my favorite part, because this should remind you of something. So we have a resistor, we have a failure rate, we have a time, and then there's 2 possible outcomes, which are complementary. And then if it fails operational, we have 3 possible outcomes, which are complementary, they add up to 1. And if it fails non-operational, there are 2 outcomes, which are complementary, that add up to 1. So if it fails operational and it's unable to fire, that's 0.01 times 0.7 times 0.3, and that's 0.0021. This is kind of like, to me, this looks kind of like a deranged decision tree, okay? That is just why you would put this failure rate. Well, I suppose I can see why you would do that, but it's really just a decision tree. So what you do is you have the severity associated with each one of these, and remember the severity 4 is the best, it's minimal, whereas 1 is absolutely catastrophic. And then we take our 3 outcomes here. So we have 0.0015 occurs twice, so that means we have 4. And we arrange them in descending order and list them underneath the least severe to most severe, so that then we have probabilities associated with least severe, with 4 through 1. There are probabilities. And those are criticality for each one of those outcomes, for each one of those severities. So it's essentially, what we've done is we've gone through all of this, and we kind of have a risk matrix, right? Because we have a probability here associated with each severity. Right? And the way that you interpret it is, it looks like, with this order of magnitude, that my probability of something really bad happening is only second to the least critical occurrence. I'd be worried about that, because that shows how close to, like I said, in this order of magnitude at least, how likely a catastrophic outcome could be if that with that resistor failing.
So there's not much of a gap between it failing with no effect and failing with catastrophic effect.
Mm-hmm.
That's what you're saying.
That's right. Yeah, at their order of magnitude. Yeah. And it's really not. Yeah, I guess it is. It is a pretty valid probability, and it's still a low probable situation. But it shows you that you have, relatively speaking, an uncomfortable likelihood of a catastrophic outcome. Now, I included this, failure modes, effects, and criticality analysis, because it is so closely related to the failure modes and effects analysis. It's basically the same thing with some data on probability, and then this decision tree, this quasi, or event tree, not a decision tree, event tree, associated with it. I think I said decision tree the first time too. Event tree is really what I meant to say. looks an awful lot like that, because let's go, if we go back and take a look at our event trees in decision analysis, just for the purposes, just for giggles, other than the way that it's displayed, which I think the FMECA is a little bit less intuitive than this, actually. Other than the way it's displayed, and especially if you look at bars, they've even got the damage state here. This looks exactly like what the FMECA did. They have a damage state. Their severity rating. They have probabilities. The only thing that they don't have is this expected, this dollar value, this monetary interpretation here. So it's kind of FMECA is kind of a hybrid between event trees and FMEA. And it's taking data and putting it into your FMEA. And then arranging it in a matrix so that you've got a risk matrix at the end of it. So it sort of takes event trees and risk matrices and FMEA and puts it all together into something that's a hybrid of all three of them. Okay. I threw this one in. This is called a fault hazard analysis. Just to show you how much like an FMEA virtually everything is, because most of the techniques, if you go through the System Safety Handbook and look at the techniques, almost all of them are variants on FMEA. This is just one of them. This is called a fault hazard analysis. Okay? Well, this looks pretty familiar. Component nomenclature, fault condition, component fault mode, subsystem. I mean, this is basically an FMEA with a lot more categories built into it. And you'll see this over and over and over. They take variants and they make it different in some very small way and then give it a different name. Like I said here, this is sometimes called a single thread analysis because they take a component and they expand it. It's an FMEA with a lot of detail in it. And that's what the single thread analysis means, is that they look at a particular component and get as much detail about that component as possible. Okay. Again, I believe that these are developed because each application has slightly different requirements, and while they're at it, they just give it a different name. That's my opinion of it anyway. One that is a little bit different, I think, and hence I'll put it here, is energy analysis, which is sometimes included in system safety, sometimes not. This is based on Haddon's energy theory. Okay? That this is an engineering approach, that all accidents are caused by contact with energy. And if we control that contact, then we will control the accidents. That's the hazard. So we have some kind of harmful energy that the person comes in contact with. And we can control it with a barrier, usually. Barrier can be physical barrier like PPE, or just separation or removal of the hazard. Okay? And the transfer rate is indicates the severity. And so it doesn't give you priorities, but it gives you a sequence, so to speak. So this is what you can do. You can alter the energy, separate the person or object from the energy, or protect the person. This is obviously a PPE of some kind. This is something like where you have a cordoned off area where a machine operates. People can't go in there. Or you alter the energy. Well, if you don't have to operate at 3 stories, If you can do it at ground level, go to ground level. That that alters the energy, so that if you fall over, you've got a scraped elbow rather than crack your skeleton. Okay, so, and here these are some examples that I took from Harms Ringdahl, which is another interesting set. Harms Ringdahl has an interesting collection of techniques, some of them system safety, some of them more traditionally occupational safety approaches. But this is one that I think is interesting nevertheless. So another way to look at it, they often categorize, and this came from Brower. Brower is pretty good too. They take energy analyses and they separate them by type. Okay? That's a reasonable way to do it, because that will lead you towards things like how to control it, because you control mechanical energy differently than you control radiant energy or thermal energy, etc. Each one of these is controlled in a different way. So this is a categorization technique. It's a classification that makes it easier to deal with the energies and how to control them, how to deal with them. And then this is a glide tank example where you have the part and you have the energies, and then you have comments on what can happen with those energies, and then some classification techniques and what to do about it. Like even here, I mean, this looks an awful lot like FMEA again, except now we're speaking in terms of Haddon's energy theory rather than in any other terms. But it's a way to classify and enumerate things that can go wrong and what to do about it. It's just that you're, like I said, you're specifically relying on Haddon's energy theory. And I wanted to close with preliminary subsystem and system hazard analysis. Again, this gets an awful lot of airtime, but really what you're doing is you are arranging your system, you're organizing it into hierarchies, so that your hierarchy allows you to get the lowest level and then analyze upwards from that. So this is the preliminary. That's the first thing we do. That's the first part of the life cycle before it even happens. And then we take our hierarchical subsystems and do all of the analyses of each of the subsystems, and then we amalgamate it into a final system analysis. This is more of a management technique, I think, than anything else. I don't think that it's a technical technique, it's a management technique that tells you what stage of the life cycle you should be doing each of these analyses. So if we look at the life cycle like this, system concept, definition, development, production, and operation, that's about where, according to Roland Moriarty, you should do your preliminary hazard analysis. Okay, that makes sense to me. That by the time you get into development, you should probably have your preliminaries done. And these are the type of things that from several different sources that you should include in it. Your energy sources, okay, Haddon's energy theory, great. Safety requirement, regulations, how the subsystems relate to each other, environmental hazards, etc. Okay, you can read those as well as I can. But they are an enumeration as best as possible of things that can happen. Then the subsystem hazard analysis, according to Roland Moriarty, should be finished by the time you begin system production, and you start it shortly after the preliminary, so it should be in parallel to preliminary hazard analysis. But you need to, by the time it goes in production, the subsystems should be very well understood. And likewise, the system. By the time it gets into production, we should have all of our But beyond the concept phase, you should have all of your systems amalgamated, your preliminaries finished, and your subsystems completed so that they can be amalgamated into the full system hazard analysis. Again, I'm mentioning this because this is like FMEA. You run into preliminary subsystem and system hazard analysis all the time. It's really just a management tool. It's a time management tool for getting through the system's life cycle. How you do the preliminary hazard analysis doesn't matter. I mean, it's whatever's appropriate. Use FMEA, fault tree, barrier analysis, whatever makes sense. And you can even apply decision analysis techniques in this because it helps you make decisions along the way. But it's a management tool. So, questions or comments? That is the end of the material I have to present to you. Okay? From now on, you'll be regaling me with your brilliance. Except for 2 weeks from now, and you'll be regaling me with your brilliance 2 weeks from now, too, during the exam. Anybody have any questions about this? Any comments on? And actually, I would find it interesting if you have comments about the way I expanded the system safety, because I expanded it beyond what most courses in system safety. I did that on purpose. And if you don't want to tell me now, at least put it in the evaluation, because I'd like to know whether you found that useful or not to take it more into the realm of operations research before we got into the actual system safety techniques. And I find that interesting to your ideas about it, whether you found it appropriate or not.
I've encountered a bunch of this stuff in the readings for the project. So I'm glad
which is from this topic, you mean?
Especially today's topics, that I can probably, I'm like armed a little bit better to go back into that reading and know what they're talking about.
Okay, good.
There's jargon associated with the world of system safety, and I think they throw that around a little easier. You know, it's a little easier to digest if you've seen it before.
Yeah. Most disciplines do develop their own set of jargon. That's the nature of them to do that.
I know when I took system safety in undergrad, we spent probably 90% of the course on what you just did today. So to get the background, I mean, we didn't do any of the math, we didn't do the probabilities, anything.
What did you talk about without? I mean, I'm just curious.
We went into a lot of detail on the different methods and different techniques for hazard analysis. There was a lot of exercises and examples. And so we basically would talk about it, and we'd have to go do it. I can't say it was all that beneficial.
It seems to me that it's so situation dependent,
right?
That it makes an exercise potentially kind of empty.
Right. We basically made stuff up.
Yeah, okay, that's what I was trying to avoid.
Yeah. So you couldn't really get any kind of benefit out of it because you were making it up as you went along to include what you had to do.
Yeah.
So I think this is a lot more beneficial going into the math.
Well, that's good.
How it works, the structure behind it.
Okay, that's good to hear. Yeah, because I ran into a lot of, when I was coming up with this class, I ran into a lot of exercises that seemed like busy work to me, and I didn't think that would be too helpful to do that, so I chose to avoid that. Okay, if no one else has any questions or comments, I'll see you next week. We'll do a lot of problems in class, and take all the questions I can. If it turns out next week that you guys would like a review, we can do a review. It's up to you whether we do one or not. I'll be available for one. And then the following week, I should be available on Monday. Okay. Thanks very much.